Okay, example 4. Here with example 4, it's basically allowing us to use exactly what the fundamental theorem of calculus was, what we did in this last example, but because this time my upper bound is x, we get to take it as is. We don't have to worry about doing any kind of substitutions. So this problem is just very simple. And if I just basically write out that theorem again, it's saying that if you take the derivative of an integral going from any value, so we'll say here 1, all the way up to x, of any kind of like basically a function of t, then what you're going to get is that exact same function just evaluated for x. Okay, so it's saying find dy dx, which I'm taking the derivative of this function then. So d dx going from 1 to x of 1 over t dt, and this rule says you're going to get this exact function back just evaluated for x. So it's just going to be 1 over x for x is greater than 0. Not necessarily greater than or equal to, so we definitely don't want the equal to part. But let's bring up that point. Why this part? You know, what's the whole purpose of that? So remember, all these rules only exist when you have a continuous function. And if I go in and I plug 0 into this function, you get undefined, so it's not continuous there. So that's why they're saying strictly greater than 0. So that way we get all the foundational rule setups where I can use these properties to make it fully continuous. Okay, example 5. We want to find dy dx. We're going to take the derivative now, again, for another function, whereas x times the integral from 2 to x squared of sine of t cubed. Okay, here in example 5, again, we're going to be taking the derivative of an integral. And if I look at this initially, I notice that it's a product. It's going to be, so we're going to be taking the derivative of x times this integral. Okay, and then even of the integral, we have an upper bound that's not just a regular x. It's going to be taking the derivative of an integral where the upper bound is x squared, so we're going to have to do our substitution. Let's first find this out then. Okay, so y prime, using our product rule, is going to be first times the derivative of the second, so d dx from 2 up to x squared of sine of t cubed dt. Okay, so that's first times the derivative of this, and then I'm going to go through and actually solve that out. First times the derivative of the second, plus the second times the derivative of the first, which is just 1. Okay, so the back term's pretty much all complete, finished. We need to work with this front one. And again, it's mainly because we want to take the derivative of an integral where my upper bound is just not x. So I want to use that fundamental theorem of calculus, part 1, but I can't. I need to change it. We need to do substitution. So let's let u equal x squared, or in this case then du dx is going to be 2x. Okay, so let's just keep working just this little piece right here. If I want to take the integral, it's going to be then the integral, if I use my substitution, to 2 all the way up to u, because now x squared is u, of sine t cubed dt, and then all of that du dx. Okay, so instead of just taking the integral, or just taking the derivative with respect to x, we're going to be taking the derivative with respect to u. Sorry, I forgot that little part. Of going from 2 to u of sine t cubed dt. Okay, this portion right here now says that I can use the fundamental theorem of calculus. So I'm going to take the derivative with respect to u, my upper bound's u. So what I'm going to get is just this exact same function as is. So sine, but instead of t cubed, it's going to be u cubed. And then we just multiply by du dx. Okay, so finishing this up just a little bit, what is u? Well, u was 2x. I'm sorry, u is x squared. So this will be sine of x squared cubed times du dx, which is 2x. Or it's going to be sine of x to the 6th times 2x. So we can even put that 2x in the front if we want. Okay. So 2x sine of x to the 6th. So what we just discovered is this portion right here replaces everything inside of these parentheses. So we want to go back and then write out our answer. To get our final answer, then we can say y prime is equal to x times 2x. We can say 2x squared sine of x to the 6th and then plus the integral from 2 to x squared of sine of t cubed dt. And there's my answer for that problem right there. All right, let's finish this up. Let's go with example number 6. We want to find the area for this specific curve, my goodness, for y equals 3x squared minus 3 from negative 2 to 2. Okay, so to perform this problem, what we want to do is, first of all, we want to do that summary on how to find the area between a graph and the x-axis. Okay, over the interval specifically, it says a to b, but we're going to go from negative 2 to 2. Okay, we want to subdivide the whole interval into the zeros. So we need to find the x-intercepts. That's the first thing. And then we're going to integrate over each subinterval, and then we're going to add the absolute values of the integrals to get the grand total. Okay, so the first thing we want to do is obviously look at a graph. So why don't we take 2 seconds and graph this thing? Well, I just went ahead and drew a tentative graph over here on the left. And if we want to find the area, we're going to take the integral basically from here's negative 2 up to positive 2. And we want to find the area. So we're looking at the area in there because it's between the curve and the x-axis. The area inside here because that's the curve and the x-axis. And then again over here. So it almost looks like we have 3 separate areas. Okay, and just to double check to make sure that these were the true x-intercepts, remember you just go 0 is equal to 3x squared minus 3, or x squared is equal to 1, so x is equal to plus or minus 1. We need to know that, because remember whenever you do your integral, what you integrate is from an x value to an x value. Okay. So subdividing up this whole overall closed interval, what we're going to do is we're going to take the integral from negative 2 up to negative 1 of our function, so 3x squared minus 3 dx, and then we're going to add on the area we get when we go from negative 1 to positive 1 of our function. And then lastly, the last little part, we're going to go from 1 to 2 of our function. Okay, so working on this basically piece by piece, obviously whenever I find one integral, I'm going to find this exact same formula for all the other ones, but let's go term by term in this first parentheses. So if I pull off the 3, and then the integral of x squared will be x cubed over 3, and then the integral of just a minus 3 will just be a minus 3, and I'll put an x because our other variable is x. And we want to evaluate this from negative 2 to negative 1. Okay, obviously those 3's are going to cancel, that's going to help. And then we can use, let me just go ahead and finish writing this one. So it's basically x cubed minus 3x evaluated from the lower bound to the upper bound. And since these bases are all the same throughout all this integration, we can almost just repeat that process for everything. So it's going to be then x cubed minus 3x evaluated from negative 1 to 1. And then again, x cubed minus 3x evaluated from 1 to 2. Okay, and just so I can allow myself just a little more room, let's go ahead and let me just erase this part down here so I can utilize my room appropriately. Okay, equals. So let's plug in always the upper bound minus the lower bounds. Okay, so going through here and plugging in the upper bounds and the lower bounds. So for this first group, okay, the upper bound plugged in, so negative 1 plugged in. Negative 1 cubed will be a negative 1, and then plus 3, minus the lower bound plugged in, should be negative 8 plus 6. Okay. In this next group, the upper bound plugged in, 1 cubed is 1, minus 3, minus the lower bound plugged in would give us a negative 1 plus 3. And the last group, upper bound plugged in will give you 8 minus 6 minus 1 minus 3. Okay, squeezing that in there. So cleaning this up, then we will get in this first parentheses basically 2 plus 2. In the next one, we're going to get negative 2, looks like minus 2, and in the third one, we'll get 2 and plus 2. Okay, So to wrap this up though, the formula says to find the total area actually is when I go through here, I'm going to be taking the absolute value of whatever comes out of these these regions. Okay, so the absolute value of 2 plus 2 is 4. Of negative 4 will be another 4. So 4 plus 4 plus 4 will give me an overall total area of 12. Okay, and so what's coming, the reason why these are all positive up here is because you're above the x-axis. This down here was all negative because you're below the x-axis and then again above. But that's why we want to take the absolute value. So the area of 4 plus 4 and 4 will give you a total area of 12.